When we talk about modern physics today, the first thing that comes to mind is the atomic bomb. Everyone agrees that atomic weapons have had a massive impact on politics. But is that really the most important influence of physics? Every new invention brings with it a new way of thinking. That way of thinking spreads among people. These new ideas inevitably clash with older traditions, religious or philosophical. In the West, people were already familiar with modern science, so their adjustment to these new ideas was easier. But in other parts of the world, the clash between science and tradition has given rise to completely new kinds of thought. This is why it is essential to explain the new concepts of physics, like quantum theory, in simple language. Quantum theory is just a small part of atomic physics, yet it completely changed the way we look at reality. It marks a radical turning point in modern science. The best way to understand it is to look at its history. Quantum theory began with the study of black body radiation. Any object, when heated, begins to glow. For example, when iron is heated, it turns red. But classical physics couldn't explain why this happens. Then, in 1900, Max Planck proposed a formula suggesting that energy is emitted in small packets called quanta. This idea was completely new and shocking because it suggested, for the first time, that energy isn't continuous. It comes in discrete chunks. Even Planck himself was surprised by this result, since it contradicted the foundations of traditional physics. Then, in 1905, Einstein extended this idea further. He showed that light itself consists of these energy packets, quanta, and used this concept to explain the photoelectric effect, where electrons are ejected from a metal surface when light falls upon it. Einstein also demonstrated that the specific heat of solids could be explained only through quantum ideas. But this raised a major confusion. Is light a wave or a particle? Even Einstein couldn't answer that question. He only said, "Perhaps the future will tell." Around the same time, Rutherford proposed his model of the atom. Electrons orbiting around a central nucleus, like planets around the sun. But classical physics couldn't explain why atoms are stable. Why don't the electrons spiral into the nucleus? In 1913, Bohr solved this by applying Planck's quantum idea to the atom. He proposed that electrons can only exist in certain discrete energy levels. This quantization explained both atomic stability and the line spectra observed in experiments. Still, Bohr's theory had contradictions. The frequency of an electron's orbit didn't match the frequency of emitted radiation. Yet Bohr's theory inspired physicists to ask deeper questions. For instance, why does radiation sometimes behave like a wave in interference patterns and sometimes like a particle in the photoelectric effect? By the 1920s, physicists were getting used to these contradictions. They knew which description worked in which context, though a fully consistent theory was still missing. However, the general idea and spirit of quantum theory were becoming clear. Physicists often designed ideal experiments, thought experiments that clarified problems even if they couldn't be done in practice. When they disagreed on theoretical possibilities, they would design simple real experiments inspired by those thought experiments. But the more they tried to understand quantum theory, the more paradoxes and confusions appeared. One example is Compton's X-ray experiment, 1923. Previously, it was believed that light waves merely make electrons vibrate and then re-emit waves of the same frequency. But Compton showed that scattered X-rays have a different frequency than the original ones. So this meant that X-rays behaved like particles colliding with electrons, transferring part of their energy and changing frequency. Thus arose a deep paradox. How can something be both a wave and a particle? In 1924, Louis de Broglie proposed that not only light, but even particles like electrons behave like waves, matter waves. This helped explain why electrons can only occupy certain stable orbits, those that fit the wavelength conditions. So now physics faced a wave-particle duality. Bohr's orbital model worked, but its logic conflicted with classical mechanics. Bohr introduced the correspondence principle, saying that at high quantum levels, farther orbits, quantum behavior merges smoothly into classical behavior. His theory wasn't exact, but an approximation pointing toward a deeper truth. The exact mathematical form of quantum theory appeared in two ways. One, matrix mechanics, formulated by Heisenberg in 1925. He replaced classical quantities like position and momentum with abstract matrices in which position and momentum couldn't both be precisely known. 2. Wave mechanics, developed by Schrödinger in 1926. He created a wave equation for the electron, successfully explaining hydrogen's energy levels. Later, Schrödinger showed that his wave theory and Heisenberg's matrix theory were actually equivalent, two mathematical languages describing the same reality. Even then, the confusion between wave and particle remained. It was now hidden beneath mathematics. In 1924, Bohr, Kramers, and Slater suggested that these waves aren't physical waves, but probability waves, describing the likelihood of finding a particle at a given location. This was a completely new and revolutionary idea. Nothing like it had ever existed in physics before. In 1926, Max Born gave this probabilistic interpretation a precise mathematical form. But these waves didn't exist in three-dimensional space. They existed in an abstract configuration space where quantities like position and momentum couldn't be simultaneously defined. Part 2. The Copenhagen Interpretation and the Nature of Reality. At one point, Schrödinger thought electrons could be treated as pure waves. But through discussions with Bohr, it became clear that this couldn't explain quantum jumps or Planck's radiation formula. By 1926-1927, physicists in Copenhagen had begun to deeply understand quantum theory. A new and extremely difficult interpretation emerged, one that was hard for everyone to accept. It seemed to imply that nature itself was absurd, but finally, the essence of quantum theory became clear through two fundamental ideas. 1. The uncertainty principle. Instead of asking, how does an experiment fit into quantum theory, physicists reframed the question. Only those experiments can occur in nature which can be clearly described by quantum mathematics. This revealed a profound limit. Quantities like position and speed cannot be simultaneously measured with perfect accuracy. Due to Planck's constant, there is a built-in limit to how precisely both can be known. 2. The principle of complementarity. Proposed by Bohr, it stated that electrons can behave as either particles or waves, but not both simultaneously. These two descriptions, though mutually exclusive, complement each other. Together, they give a complete account of physical phenomena. Through these two ideas, uncertainty and complementarity, quantum theory finally became self-consistent. This framework came to be known as the Copenhagen interpretation, which was fully clarified during Bohr's long debates with Einstein in 1927 at Brussels. It took scientists about 25 years to understand quantum theory so clearly because it required changing their entire way of seeing reality. The Copenhagen interpretation explains quantum theory through a paradox. The paradox is this: Physics experiments can only be described in the language of classical physics, yet classical language itself has limits, which the uncertainty principle exposes. We cannot discard concepts like position or velocity, but we must accept that they can never be exact. To understand this, it's crucial to compare quantum physics with classical physics. In Newtonian mechanics, if you know the position and speed of a planet, you can predict exactly where it will be in the future. But in quantum theory, even if you try to measure an electron's position and speed, they cannot both be known exactly. Instead, quantum theory gives a probability function, describing where an electron is likely to be found in the future. It doesn't predict certainty, only probability. This probability function blends two things. One is the actual fact that an electron exists somewhere, and two is our knowledge of it, which is inherently incomplete. In classical physics, measurement errors are accidental. They can, in principle, be eliminated. In quantum physics, uncertainty is fundamental. It cannot be removed because it arises from the very nature of reality. A quantum experiment always involves three conceptual steps. 1. After measurement, we define a probability function. 2. We then evolve this function over time using quantum equations. And finally, 3. We perform another measurement. The first and third steps can be described in classical language, but the second cannot. Quantum theory cannot describe what happens between measurements. It only converts possibilities into actual events when a measurement occurs. To make this clearer, physicists often use a thought experiment. Imagine trying to observe the orbit of an electron inside an atom with an extremely powerful microscope. To see the electron, you would need light of a very short wavelength, say gamma rays. But gamma rays are so energetic that when they strike the electron, they knock it out of the atom. So you could only observe the electron's position once, after which it would no longer be in its orbit. That means the electron's orbit cannot actually be observed. Therefore, it is meaningless to say that an electron exists in an orbit when it's not being measured. Quantum theory defines the electron only at the moment of measurement. In quantum physics, even calling the electron a particle isn't always appropriate. Sometimes it's better to think of it as a wave. To explain atomic radiation, for instance, describing the electron as a wave works better. But wave and particle pictures can't both be true at once. They are opposite descriptions that complete each other. Bohr called this complementarity, the idea that only by switching between these two views can we fully understand nature. Position and velocity are complementary in the same way. If one is known exactly, the other cannot be. This duality also appears clearly in the mathematics of quantum theory. Its equations can be written in either the particle form or the wave form, both correct, but mutually exclusive in interpretation. So there is no real contradiction in the dualism of quantum theory. But then comes the deeper question. What actually happens inside the atom, between observations? We can describe observations in classical physics, but we cannot describe what happens between them. The probability function only tells us what may happen, not what does happen. This introduces subjectivity into physics. An event seems to depend on whether or not we observe it. A famous thought experiment illustrates this. Imagine a screen with two tiny holes through which we pass light particles, photons, one by one. If each photon is truly a particle, it should go through one hole or the other, producing two simple spots on a photographic plate. But in reality, we get an interference pattern, showing that each photon somehow passes through both holes like a wave. So if we insist that a photon went through only one hole, we get contradictions. It means that between observations, we cannot clearly describe what happens. This is deeply strange. It suggests that observation itself changes reality. Whether an event occurs or not depends on whether we observe it. To understand this, we need to analyze the act of observation more carefully. In natural science, we never study the whole universe at once, only a small part of it. In quantum physics, that part might be extremely small, like an electron, or something larger. The size doesn't matter. What matters is that the system we observe must be distinct from the rest of the universe, including ourselves. Quantum theory always begins with two steps. First, we describe the experiment in the classical language of physics. Then we translate that description into a probability function. That function has two aspects. One is objective, the actual possibilities that don't depend on any observer. And two is our knowledge, which does depend on the observer. When the subjective part is very small, scientists call it a pure case. During the second observation, when the object, say an electron, interacts with the measuring device, a new uncertainty arises because we can never fully know the microscopic details of the measuring device itself. This uncertainty is both objective, arising from the classical description, and subjective, arising from our limited knowledge. As a result, the exact outcome of any observation cannot be predicted, only its probability. This quantum physics doesn't describe single events, but whole groups of possible events. When an observation is made, the probability function suddenly changes because our knowledge suddenly changes. This abrupt change is called a quantum jump. In other words, in quantum theory, the shift from possibility to actuality occurs only when we observe. What happens between observations cannot be described. But this change isn't caused by the mind. It happens because of the physical interaction between the object and the measuring device. Our knowledge merely catches up when the observer records the result. This leads to a profound question. Does quantum theory provide a fully objective, observer-independent description of the universe? In classical physics, scientists believed they could describe the universe without involving themselves. Quantum theory, however, divides the world into two parts, the object and the observer, or measuring apparatus. This division is somewhat arbitrary because we choose where to draw the boundary. Hence, quantum theory isn't entirely objective, since every experiment must be described in classical terms, which belong to human thought. That's why the Copenhagen interpretation begins with a paradox. We describe quantum experiments in classical language, even though we know that language is fundamentally inaccurate. Some have argued that we should abandon classical concepts altogether to eliminate the paradox. But that's impossible, because classical concepts are the refined version of the language we use in daily life. They are necessary for communication and reasoning. As Carl Friedrich von Weizsäcker said, "Nature comes before man, but man comes before science." Our way of thinking is a prerequisite for understanding nature, and that very thinking creates the paradox at the heart of quantum theory. Part 3. Ancient Philosophy and the Roots of Modern Physics. To perform a quantum experiment precisely, we must clarify its exact setup. Whenever we apply quantum theory, we divide the world into two parts, the object being studied and everything else. This division is arbitrary. We could, in principle, include the measuring device within the object itself. But even if we do that, the paradox remains, because then the measuring device must still interact with the observer, who must describe it in classical terms. So uncertainty cannot be eliminated. The measuring apparatus must be described classically, or it ceases to be a measuring device. Bohr explained that this division isn't arbitrary but realistic, because in every experiment we are interested only in a specific phenomenon. Whatever part of matter or radiation is directly connected with that phenomenon naturally becomes the object, while the measuring tool becomes part of the observer. Thus, quantum theory reminds us that we never observe nature directly. We observe it only through the questions we ask and the instruments we build. To understand the atomic world, our role as observers is essential. As Bohr once said, to understand the harmony of life, we must remember that in the drama of existence, we ourselves are both actors and spectators. The same applies in physics. In trying to understand nature, we engage it through our own questions and our own tools. The act of observation and the observer's participation becomes an inseparable part of nature's description. In ancient Greek philosophy, a fascinating question was asked: is the world made of one known substance, like water, air, or fire, or of something entirely unknown and different? That very question still echoes in modern atomic physics. Today's scientists ask, are all elementary particles, protons, electrons, mesons, made of a single fundamental entity, or are they composed of something entirely unknown? In recent years, most physicists have tended to believe that a few known particles are fundamental, and all others are built from them. But I believe the second idea is more correct, that there exists a universal substance, which we may call energy or matter, that is truly fundamental. This idea resembles that of the ancient philosopher Anaximander. In early Greek thought, Anaximenes, another Milesian philosopher, proposed that the basic substance of the world is air. When air condenses, it becomes clouds and water. When it rarefies, it becomes fire. Then, Heraclitus declared that the world's fundamental substance is fire, because fire is always moving and the world is always changing. He said that opposites, hot and cold, pleasure and pain, are constantly in conflict, and that their tension creates harmony. The world, therefore, is both unity and diversity at once. Its unity arises precisely from the tension between opposites. Modern physics, in many ways, is close to Heraclitus's vision. If we replace the word fire with energy, we find the same concept. Energy is the essence from which the entire universe is made, and it is always in motion. Energy transforms into motion, heat, light, and force. We will explore this modern parallel more deeply later. After Heraclitus, Parmenides proposed that the world is one permanent reality that never changes. For him, change was an illusion, since change would require empty space, and he denied the existence of emptiness. But this idea couldn't explain the diversity of the world. Then, Empedocles suggested that the world is made not of one substance, but of four fundamental elements: earth, water, air, and fire. These combine and separate under the influence of two forces, love and strife. All change, he said, arises from the interplay of these forces. Empedocles' idea marked the first clear step towards materialism, the belief that the world is composed of physical substances. These substances, in different combinations, create all the variety we see. Later, Anaxagoras proposed that the world contains an infinite number of seeds, each infinitely small. These seeds constantly mix and separate, producing change. He imagined them like grains of colored sand, endlessly combining and separating. He also said that mind, or nous, or intelligence, is the force that organizes this motion. Then came the revolutionary idea of Leucippus and Democritus, the concept of the atom. They argued that the world is made of tiny, indivisible particles called atoms, which are eternal and unbreakable. Atoms move through empty space. Thus, reality consists of two things: atoms, which exist, and void, which does not, the empty space through which atoms move. This void was essential to explain motion. Democritus taught that all atoms are made of the same substance, but differ in size and shape. Atoms themselves have no color, taste, or smell, just like Democritus's atoms, but they also lack fixed geometry or motion. Their exact description is only a probability function, meaning it doesn't actually exist in a fixed way, but only as a tendency to exist. Thus, modern particles are even more abstract than Democritus's atoms. Democritus believed all atoms were made of the same substance. Modern physics agrees in a sense. All elementary particles possess mass. Einstein's theory of relativity showed that mass and energy are equivalent, two forms of the same thing. Therefore, modern physics concludes that all particles are made of energy. In this sense, energy is the fundamental substance of the universe, because energy can never be destroyed. This idea parallels Heraclitus's fire, since for him, fire was the source of all change, and in modern physics, that role belongs to energy. However, Democritus believed atoms were indestructible, eternal, and unchanging. Modern physics disagrees. Elementary particles can transform. In high-energy collisions, old particles can be destroyed and new particles created. Experiments confirm this transformation. So all particles are made of the same substance, energy. In this sense, modern physics is closer to Plato and Pythagoras than to Democritus. For Plato, the fundamental entities of the world were not material, but mathematical forms. Pythagoras said, "The world is number." In Plato's time, mathematics dealt mainly with geometric shapes, triangles and regular solids. In modern quantum theory, too, particles are ultimately mathematical forms, though far more complex. Plato's forms were static and fixed. Modern physics is dynamic. Since Newton, physics has been about the laws of motion, not shapes. Today, we still don't know the ultimate fundamental law of motion, but physicists believe it will take the form of a highly complex mathematical equation describing not particles, but a field of waves. The solutions to that equation, the eigensolutions, would correspond to the elementary particles themselves. Just as in Pythagoras' theory of music, where distinct vibrations of a string create musical notes, here the universe arises from the vibrations of an underlying field, only far more intricate. Physicists hope that this fundamental law will be mathematically simple, because all basic laws of nature discovered so far are. But there is no proof of this, only faith that nature's deepest truths are elegantly simple. Some ask, if elementary particles can be created in collisions, how can they be called indivisible? The answer is that in such collisions, what divides is not the particle itself, but energy, which simply rearranges into new particles. So the elementary particle, as a form of energy, remains indivisible. Part 4. From Greek thought to Descartes and modern science. After the great age of Greek philosophy ended, science slept for nearly 2,000 years. When it reawakened in the 17th century, it returned with new energy and a new foundation. That foundation was laid by René Descartes, 1596 to 1650. Descartes, like the Greeks, wanted to find a firm basis for all knowledge. He began by doubting everything that could possibly be doubted: his senses, his beliefs, even his own body. But he realized there was one thing he could not doubt: his own act of thinking. From this, he concluded, cogito ergo sum. I think, therefore I am. This became the cornerstone of modern Western philosophy. From that point onward, Descartes divided reality into two distinct realms. 1. Res extensa, extended substance, or matter, existing in space. 2. Res cogitans, thinking substance, or mind, which has no spatial extension. Matter, for Descartes, was completely mechanical, a vast machine composed of inert parts that move according to deterministic laws. He imagined the universe as a great clock, set in motion by God, but running automatically thereafter. Mind, on the other hand, was non-material. It thought, reasoned, and willed, but had no physical existence. Thus began the Cartesian dualism between mind and matter, subject and object, consciousness and substance. This division shaped all of Western thought for centuries. Isaac Newton completed this mechanistic vision. In Newton's physics, the universe was a giant system of moving particles obeying mathematical laws of motion and gravitation. Every event had a cause. Every effect followed deterministically. If one knew the positions and velocities of all particles at a given time, one could predict the entire future of the universe. This deterministic view was absolute. Even human thought and behavior seemed to fit into this grand mechanical order. Nature became an object, something outside the observer, to be measured, manipulated, and controlled. This picture was so successful that for over 2 centuries it defined the very meaning of science. The laws of Newtonian mechanics explained everything from falling apples to planetary motion. They provided a framework for chemistry, engineering, and even economics. But by the late 19th century, cracks began to appear in this great machine. 3 discoveries shook the foundations of classical science. 1. The electromagnetic field of Faraday and Maxwell, which showed that empty space wasn't empty at all. It had structure and energy. 2. The theory of relativity, Einstein 1905 to 1915, which destroyed the idea of absolute space and time. 3. The quantum theory, which revealed that nature behaves discontinuously, probabilistically, and unpredictably. Einstein and the relativity of space and time. Before Einstein, physicists believed in an invisible medium called ether filling all space, through which light waves propagated. But the Michelson-Morley experiment, 1887, failed to detect any trace of motion relative to this ether. Einstein boldly discarded it altogether. In his special theory of relativity, 1905, Einstein showed that space and time are not separate and absolute. They are parts of a single 4-dimensional continuum, space-time. Events that seem simultaneous to one observer may not be simultaneous to another moving observer. The speed of light, c, is the same for all observers regardless of motion. From this, Einstein derived the most famous equation in physics. Energy and mass are equivalent. Matter is condensed energy. Thus, matter and energy are no longer 2 separate substances, they are 2 forms of the same underlying reality. In his general theory of relativity, 1915, Einstein went further. Gravity is not a force acting across space, but the curvature of space-time itself. Matter tells space how to curve. Curved space tells matter how to move. This elegant vision united matter, motion, and geometry. It also showed that the universe is dynamic, expanding, contracting, and evolving. But relativity still preserved determinism. Given initial conditions, the future could still, in principle, be calculated exactly. Quantum theory, however, would destroy that last remnant of the Newtonian dream. The quantum revolution and the end of determinism. Quantum theory began as a correction to classical physics, but ended up overturning it entirely. Planck's discovery of energy quanta, Einstein's photoelectric effect, and Bohr's atomic model all hinted that energy and matter behave in discrete steps. By the 1920s, Heisenberg and Schrödinger formalized the new mechanics. Heisenberg's matrix mechanics focused on observable quantities, rejecting all talk of invisible paths or orbits. Schrödinger's wave mechanics described matter as waves spread out in space. The two were later shown to be mathematically identical, but conceptually they led to a profound question: what is the true nature of reality? In quantum theory, reality does not exist in a definite state until it is observed. Before observation, all possibilities coexist, like waves of probability. When an observation is made, one possibility becomes actual, and the rest vanish. This contradicted every intuition of classical science. Einstein refused to accept it. He famously said, "God does not play dice with the universe." Bohr replied, "Stop telling God what to do." The Copenhagen interpretation, led by Bohr and Heisenberg, argued that physics can only describe what can be observed, not what really exists beyond observation. Quantum theory, they said, doesn't tell us what the world is, but what we can say about it. Thus, physics became not a description of reality itself, but a description of our interaction with reality. This shift shattered the Cartesian division between subject and object. The observer could no longer be separated from the observed. Every measurement involved both. The act of observation became part of the phenomenon. Einstein tried to resist this idea all his life, proposing thought experiments to expose quantum theory's incompleteness. But each time, quantum theory survived, often with even deeper insight. Today, experiments on quantum entanglement confirm that particles separated by vast distances can remain mysteriously correlated, as if reality itself is non-local, connected beyond space and time. The collapse of mechanistic materialism. With relativity and quantum theory, the old mechanistic worldview collapsed completely. In classical physics, the universe was like a giant clock, predictable, absolute, and objective. In modern physics, the universe resembles a web of interconnections, dynamic, probabilistic, and participatory. Matter is no longer seen as inert stuff, but as energy in motion, structured by laws that are themselves abstract patterns, mathematical relationships rather than mechanical forces. Space and time are not passive containers, but active participants. Observation is not a neutral act, but a creative one, bringing potential into actuality. Thus, modern physics doesn't return us to the naive materialism of the past. It brings us closer to a philosophy of unity, a vision in which mind and matter are interwoven aspects of one underlying reality. Part 5. The Unity of Energy and Matter, Toward a Philosophical Synthesis. The idea that matter and energy are one is not just a scientific principle. It is a profound philosophical truth that changes how we see the entire universe. In classical physics, matter was thought to be composed of hard, indestructible particles. They interacted through forces that acted across empty space. But with Einstein's theory of relativity and the rise of quantum mechanics, this picture completely changed. Matter turned out to be nothing more than a condensed form of energy. Every particle, from the smallest electron to the heaviest nucleus, can transform into energy, and energy can, under certain conditions, condense back into particles. This means that the so-called substance of the universe is not solid at all. It is dynamic, flowing, and inherently process-based. We can no longer speak of matter as something separate from energy. Matter is energy, temporarily appearing as form. It is like a whirlpool in a river, a pattern that appears stable, yet is made entirely of moving water. The whirlpool seems to be a thing, but it is really just a process within the flow. Similarly, all matter is a process within the flow of energy. Every atom is a vibration, a pattern sustained by dynamic balance. The universe is not a collection of objects, but a web of interconnected processes. Nuclear physics and the conversion of matter into energy. This truth was revealed dramatically through the study of nuclear reactions. In ordinary chemical reactions, only the outer electrons of atoms are rearranged, and the energies involved are small. But in the nucleus, the situation is different. The forces holding protons and neutrons together are enormous, millions of times stronger than chemical bonds. When the nucleus changes, as in radioactive decay or nuclear fission, a small amount of matter disappears and a huge amount of energy appears in its place. This is what happens in an atomic bomb, and also in the sun, where nuclear fusion converts hydrogen into helium, releasing vast amounts of energy. Einstein's equation E equals mc squared shows why this happens. Even a tiny mass corresponds to enormous energy, because the speed of light, c, is so large. A single gram of matter, if converted entirely to energy, could power an entire city for days. In nuclear reactions, matter and energy continually transform into each other. Particles collide, annihilate, and reappear. Nothing truly solid remains, only a constant transformation of form. Thus, the modern physicist sees the world not as a collection of fixed substances, but as a dynamic dance of energy, forever creating and dissolving patterns. The world as a web of relationships. Quantum field theory goes even further. It teaches that even particles are not fundamental entities. They are excitations, small localized vibrations of underlying fields that pervade all space. The electron, the photon, the quark, each is simply a ripple in a different field. When the ripple subsides, the particle disappears. What remains is the field itself, which is continuous and omnipresent. Therefore, at the deepest level, there are no things, only relationships. Reality is an intricate network of interactions, like the threads of a spider's web, each point defined only through its connections with others. In this view, the distinction between object and observer loses meaning. Every observation is an interaction, a relationship between two parts of the same whole. The observer and the observed are woven into a single fabric of being. This view also dissolves the old idea of isolation. No particle, no system, no living being exists independently. Everything is connected. Every change reverberates through the entire web of existence. Energy as the essence of reality. If we ask what this energy truly is, physics gives no concrete answer. Energy cannot be seen or touched. It can only be measured by its effects. It is, in essence, a capacity for change. Energy is the universal potential, the creative force that becomes light, matter, motion, and life. It is what Heraclitus called fire, what Indian philosophy called Shakti or prana, what Chinese sages called qi. The language is different, but the intuition is the same. In every transformation, from the burning of wood to the shining of stars, the same principle holds. Energy never disappears. It only changes form. At the deepest level, the universe is not made of matter, but of motion, of energy perpetually unfolding. When energy manifests as form, we call it matter. When it moves freely, we call it radiation. When it organizes itself into awareness, we call it life and mind. But all these are just different states of one and the same reality. The return to unity. Thus, modern physics, after centuries of dividing and dissecting, has come full circle, returning to a vision of unity. The ancient philosophers intuited this unity through metaphysical reasoning. Today, science confirms it through experiment. The distinction between matter and spirit, object and subject, is no longer absolute. Mind and matter are not two separate realms, but two aspects of one underlying whole. In the dance of energy, there is no observer outside the universe. The observer is part of the dance. Reality is participatory, self-aware through us. When a scientist studies the world, the universe studies itself. When we seek truth, it is the cosmos reflecting upon its own being. Conclusion: from fragmentation to wholeness. From Einstein's relativity to quantum theory and nuclear physics, every step of modern science has brought us closer to a single truth, that the universe is not made of things, but of relations, not of matter, but of energy in motion. The great illusion of separateness between mind and matter, between self and world, dissolves in this light. Every atom in our bodies was once part of a star. Every breath we take is shared by countless living beings. We are not observers standing outside the universe. We are expressions of the universe itself. This realization, born from the deepest insights of physics, fulfills what the ancient sages intuited long ago, that all is one, and that the essence of that oneness is energy, eternal, indestructible, ever-changing, yet always the same. The final message of modern physics, then, is not one of cold mechanism, but of living unity. Matter, mind, and motion are three faces of one cosmic process, the ceaseless flow of existence itself. Part 6. Competing interpretations of quantum theory and the limits of knowledge. Even after the Copenhagen interpretation became the dominant view, not everyone accepted it. Einstein, de Broglie, and later David Bohm continued to insist that quantum mechanics must be incomplete. They believed there must exist hidden variables, unknown factors that determine the behavior of particles with perfect precision, even if we can't yet measure them. Einstein's objection was simple but profound. He could not believe that God plays dice with the universe. For him, physical reality had to exist independently of observation. The moon, he said, must exist whether or not we look at it. In 1952, David Bohm revived de Broglie's pilot wave theory and gave it mathematical precision. According to Bohm, every particle has a definite position and velocity guided by a hidden quantum potential. This potential, though invisible, determines the trajectory of each particle. In Bohm's model, the apparent randomness of quantum events arises not from chance, but from our ignorance of these hidden factors. At first glance, Bohm's theory seems elegant. It restores determinism and realism. But it has a cost. It must accept non-locality, meaning that distant events can influence one another instantaneously, violating the spirit of relativity. Bohm's universe is not mechanistic, but holistic. Every part is connected to every other part by invisible relationships. Ironically, while Bohm's theory was meant to restore the old order of causality, it actually deepened the mystery of connectedness. It replaced randomness with an unseen unity. Some physicists found this beautiful. Others called it metaphysics disguised as physics. The Copenhagen interpretation, on the other hand, avoided hidden mechanisms altogether. It refused to describe what happens between observations, not because it is unimportant, but because it is unknowable. In Bohr's view, physics is not about what is, but about what can be said. The purpose of science is not to uncover ultimate reality, but to describe patterns in experience. Bohr insisted that trying to picture what an electron really is between measurements is meaningless. The only meaningful statements are about measurable quantities, what we can actually observe. Thus, quantum mechanics describes not reality itself, but the relationship between observer and phenomenon. Einstein never accepted this. He demanded an objective world that exists independently of observation. But the experiments of later decades, especially those testing Bell's inequalities, showed that quantum predictions match nature exactly, while any hidden variable model that preserves locality fails. It seems that nature really does behave as quantum mechanics describes: probabilistic, interconnected, and observer-dependent. The meaning of probability and the nature of reality. In quantum theory, probability does not express ignorance in the classical sense. In classical statistics, say when tossing a coin, the outcome is random only because we lack complete knowledge. In principle, if we knew all initial conditions, we could predict the result exactly. In quantum mechanics, probability is different. It is fundamental, not a reflection of ignorance, but a property of nature itself. No deeper description exists beneath the quantum wave. Reality, at its core, is potential until observed. This was the hardest lesson for physicists to accept, that reality is not deterministic, but a realm of possibilities that become actual only in interaction. The philosopher Werner Heisenberg described it beautifully. Atoms and elementary particles are not things, they are tendencies, tendencies for something to happen. Thus, the physical world is not made of solid entities, but of events, interactions, and probabilities. Matter, energy, and even space-time emerge from these processes. Beyond objectivity, the role of the observer. In classical science, the observer was separate from the world. The scientist's job was to measure without disturbing, to see the world as it is. But quantum theory shattered that illusion. In the microscopic realm, observation changes the observed. When an observer measures an electron's position, the electron's wave function collapses into a definite state. That collapse is not caused by the observer's mind, but by the interaction between measuring device and object. However, this very interaction means the observer can never stand outside the system. Thus, in quantum physics, the subject-object distinction dissolves. There is no observation without participation. Reality is co-created by observer and observed. This realization deeply influenced 20th century philosophy. Thinkers such as Whitehead, Heisenberg, and Weizsäcker began to see the universe not as a machine, but as a process of becoming, a living, self-organizing whole in which consciousness and matter are interwoven. This transformation of thought also changed our view of human freedom. In the deterministic universe of Newton, everything, even human thought, was governed by mechanical laws. Free will was an illusion. But in the quantum universe, indeterminacy is built into the fabric of reality. Events are not fixed in advance. They exist as probabilities that unfold through interaction. Freedom is not the absence of law, but the openness of potential. Einstein saw this indeterminacy as chaos. Bohr saw it as creative harmony. Where Einstein said, "God does not play dice," Bohr replied, "It is not for us to tell God how to run the universe." The limits of language. The strangeness of quantum theory arises not only from nature itself, but from the limitations of our language. Our everyday words like particle, wave, position, time are based on classical experience. They cannot fully capture a reality that behaves outside human intuition. Bohr often reminded his students that language shapes thought. We must use classical terms because they are the only ones we have, but we must also remember their limits. Physics, he said, is not a description of how nature is, but of what we can say about nature. As physicist John Wheeler later put it, "No phenomenon is a real phenomenon until it is an observed phenomenon." This is not idealism in the old philosophical sense. It doesn't mean that reality only exists in the mind, but rather that the act of measurement is part of the structure of reality itself. The world is not a fixed stage upon which events play out. It is a dynamic web in which measurement, interaction, and existence are inseparable. Part 7. The Evolution of Physics, from Atoms to Fields to the Cosmos. When we trace the evolution of modern physics, we see a journey from solidity to subtlety, from matter to energy, and from energy to information. In the early stages of science, the atom was considered the ultimate building block of reality, an indivisible, eternal unit, just as Democritus had imagined. But as experimental methods improved, the atom itself dissolved into a new hierarchy of smaller entities: electrons, protons, neutrons, and later, quarks, neutrinos, and other fleeting particles. Each discovery seemed to bring us closer to the foundation of matter, yet with every step, the foundation itself became less tangible. The deeper physicists probed, the more the solid world of classical intuition faded into a field of probabilities, vibrations, and relationships. By the mid-20th century, physicists no longer thought of particles as tiny marbles bouncing through space. They began to see them as excitations of underlying fields, energy patterns, rather than material objects. In this new picture, every type of particle corresponds to a different quantum field that fills all of space. The electron is a ripple in the electron field, the photon a ripple in the electromagnetic field, and so on. What we call empty space is not empty at all. It is a seething ocean of potential energy, alive with virtual particles appearing and disappearing. Thus, the solid world of Newtonian matter has vanished into a dynamic web of fields and fluctuations. Reality is no longer composed of things, but of processes. Nuclear physics and the birth of the atomic age. In the early 20th century, with the discovery of radioactivity, humanity learned that matter can spontaneously transform into energy. Einstein's E=mc² gave this transformation its mathematical expression. Then, with the discovery of nuclear fission, that formula became terrifyingly real. In fission, a heavy nucleus, such as uranium or plutonium, splits into lighter nuclei, releasing enormous energy. In fusion, light nuclei, such as hydrogen, combine to form heavier ones, as in the Sun. Both processes revealed the same truth, that a small reduction in mass produces vast quantities of energy. These discoveries not only reshaped science, but also transformed human civilization, for better and for worse. They gave us both nuclear power and nuclear weapons, reminding us that knowledge without wisdom is a dangerous force. Through these reactions, physicists witnessed directly the interconversion of matter and energy. The ancient idea that all is fire, or energy, was now measurable in laboratories. Thus, the dream of Heraclitus found experimental proof. The world is an ever-living flame, transforming yet eternal. From atomists to cosmologists. After mastering the atom, physicists turned their gaze to the universe itself. Einstein's general relativity provided the mathematical framework for understanding the cosmos. It revealed that space and time are not passive backgrounds, but dynamic entities that curve, stretch, and evolve. The discovery that the universe is expanding, confirmed by Edwin Hubble in 1929, was a direct consequence of Einstein's equations. This led to the Big Bang theory, which proposed that the universe began as an incredibly dense and hot state roughly 13.8 billion years ago. At that initial moment, all matter, energy, space, and time were unified in a single point, a singularity. In that sense, modern cosmology also returns to a kind of philosophical monism. Everything that exists emerged from one common origin. Later, quantum theory entered cosmology, suggesting that even the birth of the universe involved quantum fluctuations. Tiny variations in the early energy field eventually formed galaxies, stars, and planets. Thus, the same principles governing the microcosm, the atomic world, also govern the macrocosm, the universe itself. The laws that describe the dance of electrons in an atom also describe the motion of galaxies in the heavens. The search for unity. Throughout the history of physics, scientists have sought unity, one law that could explain all phenomena. Newton unified celestial and terrestrial motion. Maxwell unified electricity and magnetism. Einstein unified space and time. Now physicists seek to unify quantum mechanics and general relativity, the laws of the very small and the very large. Several attempts have been made. Quantum field theory unified three fundamental forces: electromagnetism, the weak, and the strong nuclear forces. Electroweak theory showed that electricity and the weak force are two aspects of a single interaction. Quantum chromodynamics unified forces except gravity. Grand unified theories aim to merge all forces except gravity. String theory and loop quantum gravity go further, seeking to unify everything, matter, energy, space, and time, into one fundamental framework. According to string theory, all particles are not points, but tiny vibrating strings of energy. Different vibrational modes produce different particles, just as different musical notes arise from one instrument. In this sense, the entire universe is a cosmic symphony, composed of vibrations playing across multi-dimensional space-time. While still speculative, these theories continue the age-old quest for unity, a single principle underlying all forms and forces. From matter to mind, the expanding horizon. As physics unifies the external world, it inevitably turns toward the inner world, the realm of consciousness. If the observer cannot be separated from the observed, then understanding the universe must also involve understanding the mind that perceives it. Some modern thinkers have begun to see parallels between quantum physics and ancient spiritual philosophies, not as pseudoscience, but as convergent intuitions about unity and interdependence. The Upanishads, for instance, speak of Brahman, the infinite reality manifesting as all forms. Modern physics speaks of an energy field that manifests as particles and waves. Both point to the same fundamental insight: the world is one, and diversity is only its expression. This does not mean science and spirituality are the same. Their methods differ profoundly. Science tests through experiment, spirituality through direct inner experience. But both, in their deepest moments, encounter the mystery of oneness, a reality that transcends the boundaries of the observer and the observed. Part 8. The ethical and philosophical implications of science. With the advent of nuclear physics, science crossed a threshold it could never retreat from. For the first time in history, humanity acquired the power to annihilate itself, to erase entire cities with a single flash of light. The same intellect that sought truth now held the capacity for total destruction. This moment revealed something profound. Science is not inherently good or evil. It is a tool, an extension of the human mind, and thus it inherits our virtues and our flaws. If guided by wisdom, science becomes a means of liberation, freeing us from ignorance, disease, and poverty. If driven by greed, pride, or fear, it becomes a weapon. The ethical question, then, is not about the science itself, but about the spirit that wields it. Power and responsibility. When Rutherford split the atom, he reportedly said, "Anyone who expects a source of power from the transformation of these atoms is talking moonshine." Yet within a few decades, his discovery powered both cities and bombs. This paradox, that knowledge meant to enlighten can also destroy, defines the modern age. It demands of scientists not only intellect, but moral imagination. Einstein himself, who laid the theoretical foundation for nuclear energy, later lamented the use of his discoveries for war. He wrote, "The unleashed power of the atom has changed everything except our way of thinking." That, he said, was humanity's greatest danger. If science expands power but not conscience, civilization becomes technologically advanced yet spiritually primitive, a child with a loaded weapon. Thus, the task before humanity is not merely to know more, but to become wiser. We must learn to align scientific progress with ethical evolution. Science and society. Every major scientific revolution has also been a social revolution. The printing press democratized knowledge. The Industrial Revolution transformed economies. The digital revolution reshaped human communication. Now, the atomic and quantum revolutions are transforming power itself, political, economic, and psychological. The nations that master science gain dominance. Those that lag become dependent. This dynamic creates not only progress, but also inequality between rich and poor, between powerful and powerless. If science is monopolized by a few, it becomes a form of control. If shared, it becomes a path to freedom. Therefore, the true measure of a scientific civilization is not how advanced its machines are, but how justly its knowledge is used. The limits of scientific knowledge. No matter how far science advances, it must always remain aware of its boundaries. The scientific method can describe how things happen, the mechanisms, the laws, the probabilities. But it cannot tell us why existence is at all, or what purpose, if any, underlies it. Physics can explain the birth of the universe, but not why there is something rather than nothing. Biology can describe how life evolves, but not why consciousness feels joy or sorrow. In this sense, science maps the structure of reality, while philosophy and art explore its meaning. To forget this distinction is to mistake knowledge for wisdom. Wisdom arises not from data, but from reflection, from the ability to see the human condition in its wholeness. It comes when intellect humbles itself before mystery. The future of understanding. Modern physics has already humbled us. It shows that what we call matter is mostly empty space, that time is not absolute, that observation itself alters reality, and that uncertainty is not ignorance, but a fundamental feature of the universe. These revelations are not merely technical, they are existential. They tell us that certainty is an illusion and that humility is the beginning of knowledge. Perhaps this is the hidden gift of modern science, to dissolve our arrogance, to remind us that we are not masters of nature, but participants in its unfolding. We are not observers standing apart, but waves in the same cosmic sea. Science and culture, the meeting of worlds. Modern science spreads beyond its European origins and encounters diverse cultures with ancient spiritual heritages: India, China, Japan, the Islamic world. This encounter is not a clash, but a conversation. When Western rationalism meets Eastern introspection, when analysis meets contemplation, a richer understanding may emerge. Science can learn from the spiritual insight that all phenomena are interconnected, and spirituality can learn from the scientific rigor that insists on evidence. In this meeting, humanity has a chance to reconcile reason and reverence, knowledge and wisdom. As Heisenberg once said after visiting India, "I think the great philosophical ideas of the East are going to have a profound influence on the West." The responsibility of knowledge. Every generation must rediscover one truth: the universe does not bend to our desires. It follows its own laws, beautiful, impartial, and unforgiving. To understand those laws is to gain power, but to use that power rightly requires self-knowledge, the hardest kind of knowledge. Science gives us wings, but ethics must tell us where to fly. Otherwise, the higher we soar, the greater our fall. Thus, the final challenge of modern physics is not mathematical, but moral. The question is no longer, what is the world made of, but what kind of world do we wish to create? Epilogue. The new vision. In the end, the story of science is the story of consciousness itself, of humanity awakening to its own reflection in the cosmos. Each discovery expands not only our power, but our sense of wonder. We have learned that we are made of stardust, that our atoms were forged in ancient suns, that the light we see began its journey millions of years ago, and that the same laws govern both galaxies and human thought. In this vast and intricate universe, we are both insignificant and essential, a brief expression of cosmic intelligence learning to know itself. So perhaps the true destiny of science is not control, but understanding, not domination, but participation, not conquest, but communion. And in that realization, that the knower and the known are one, the ancient wisdom and the modern science finally meet. Part 9. Language, Logic, and the Human Quest for Meaning. Modern physics not only revolutionized our understanding of nature, it also shook the very language we use to describe it. Words that once seemed precise, particle, wave, space, time, no longer fit. Each discovery forced scientists to invent a new vocabulary or twist old terms into unfamiliar meanings. This linguistic crisis was not a minor issue. It struck at the foundation of how humans think. Because thought itself depends on language, and if language fails, thought becomes uncertain. The limits of language. Everyday speech evolved in the prehistoric world to describe solid objects, visible motions, familiar sensations. But quantum phenomena are not solid, visible, or familiar. They occur in realms where classical concepts simply break down. When physicists say an electron is both a particle and a wave, they are using metaphors, words stretched beyond their original meaning. We must speak this way because human language has no words for something that behaves like both and yet like neither. As Niels Bohr put it, we are suspended in language in such a way that we cannot say what is up and what is down. The word reality itself cannot be used without quotation marks. Thus, the quantum revolution was not merely physical, it was semantic. It forced us to confront the fact that our words are tools, not truths. The logic of the uncertain. Classical logic rests on two ancient laws. 1. The law of non-contradiction. A statement cannot be both true and false. 2. The law of the excluded middle. A statement must be either true or false, never both, never neither. But quantum physics violates both. An electron may be here and there, or neither here nor there, until measured. Reality does not conform to the binary logic of yes or no. To capture this, some philosophers of science proposed a new kind of logic, quantum logic, where truth is not absolute but graded, ranging continuously between 0 and 1, like probability. In this logic, statements are not fixed propositions, but tendencies, possibilities waiting to be realized. This mirrors the behavior of quantum systems themselves, which exist as potentialities, not as definite facts, until observation. Thus, the mathematics of probability becomes a new kind of ontology, describing not what is, but what might be. From facts to potentials. In classical science, facts were sacred. Something was either observed or not, true or false, real or unreal. But in modern physics, the line between potential and actual has blurred. The quantum world is a world of becoming, not of being. It contains patterns of probability, waves of potential that occasionally crystallize into facts through interaction. In this sense, reality is not a fixed picture, but a continuous process of actualization. What we call facts are simply the moments when possibility becomes manifest, when the universe chooses. The philosopher Werner Heisenberg described this as the transition from potentia to act, borrowing Aristotle's language. In Aristotle's view, every actuality arises from potentiality. In quantum theory, that ancient insight becomes literal physics. Thus, the boundary between science and philosophy dissolves once again, for both now speak the same language of possibility. language and consciousness. If observation plays a constitutive role in reality, then language, the form in which observation is expressed, also shapes what is real for us. We do not merely describe the world, we construct its intelligible version through linguistic frameworks. This means that every scientific theory is also a metaphor, a structured way of seeing. Change the language, and the world appears differently. Einstein's universe of curved space-time required abandoning the language of absolute simultaneity. Quantum theory required abandoning the language of deterministic cause. In each case, new language reshaped what we could even imagine to be true. Therefore, the evolution of science is inseparable from the evolution of language itself. The incomplete circle. Modern physics has not answered every question. It has, in fact, generated new ones, deeper, subtler, and more disturbing. But perhaps that is the point. If the universe were entirely comprehensible, it would not include beings capable of wonder. Our ignorance is not a defect. It is the space in which understanding grows. As Bohr said, the opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth. Reality, it seems, is not a single truth, but a harmony of opposites.
The final insight. After all the equations, experiments, and philosophical debates, one realization remains. Knowledge is participatory. The observer is not separate from the observed. The knower and the known are aspects of one unfolding event, the universe knowing itself. Language, logic, and science are tools in this great act of self-awareness. They do not capture the whole, but they point toward it. Perhaps that is all we can ask for. Not final answers, but deeper questions. Not the conquest of mystery, but communion with it. And in that sense, the story of physics, from the atom to the cosmos, is not just about matter or energy, but about meaning, the ancient, endless dialogue between mind and universe.